Hi, welcome to my class in Advanced Statistics. Today we will take up random variables, two categories of random variables, and probability distribution of a discrete random variable. First, we start with experiment. In Statistics 1, we define experiment as any activity that generates data. Now, we formally define experiment as a process by which observation is obtained. Experiment is a process by which observation is obtained. Now, these observations we obtain from experiments form the basis of the inferences or conclusions we make. And these inferences focus on the characteristics or variables of the elements or members of the population. These characteristics or variables can be categorized into two categories of variables. Number 1, quantitative variable. Number 2, qualitative variable. We start with quantitative variable. A quantitative variable takes numerical values, and examples of quantitative variables would be the closing price of a stock in the Philippine Stock Exchange, the number of barrels of crude oil produced from an oil well, the number of COVID patients who recovered from the disease on a monthly basis, while the qualitative variable would refer to the properties or attributes or qualities of the elements or members of the population. Examples of qualitative variable would be the ratings of a TV show as for general patronage, for parental guidance, or for adults only. Also, another example would be the classification of a finished product in a production or manufacturing company, particularly in the quality control department, where the finished items are classified as passed for quality or rejected for quality. Another example would be the make or brand of car or automobile. Generally, in most experiments, observations are assigned numerical measurements. And these numerical measurements are represented by variables. For example, if we represent x, the numerical measurement for an experiment, the values of x may vary according to some probabilistic or random mechanism. We take a specific example. Consider the following experiment. Consider the experiment of tossing, rolling a die. A die, as you may know, is a cube with 6 faces, and in each face there is a number of dots. And in this experiment, we are interested in the number of dots that appear on the upper face of the die after we toss or roll the die. Since the number of dots on the faces of the die vary from numbers 1 2, 3, up to 6, that is the number of dots can be 1 or 2 or 3 up to 6, we can represent the number of dots on the upper face of the die by a variable, say x. We let x represent the number of dots on the upper face of the die. We let x represent the number of dots on the upper face of the die. And we obtain this number of dots on the upper face of the die by counting. And this variable x is an example of quantitative variable. Now, as I said, the values of x, the variable x can take values from 1 to 6. The variable x can take values from 1 to 6, or any one of these 6 possible values, because in each toss of a die you can get 1 dot or 2 dots or 3 dots up to 6 dots. But the value of x depends on the what we call probabilistic or random mechanism, because the event of getting one of these 6 possible outcomes is a random event. Now, this quantitative variable x is what we call an example of random variable. Again, this example, this variable x that represent the number of dots on the upper face of the die when we toss a die is an example of random variable, because its values depends on the outcome of the experiment of tossing the die. And these outcomes of this experiment of tossing a die are random events. We now formally define random variable. A variable x is a random variable if the value it assumes corresponding to the outcome, to an outcome of an experiment, is a chance or random event. Again, a variable such as this variable x is a random variable if the value that it assumes corresponding to the outcome of an experiment is a chance or random event. We now formally define random variable. Random variable. A variable x is a random variable if the value it assumes corresponding to an outcome of an experiment is a chance or random event. The definition of random variable says that each value that a random variable takes or assumes corresponds to one specific outcome of an experiment. And this outcome is a random or chance event. From our statistics 1, we define event as a subset of the sample space, and we define sample space as the set or collection of all possible outcomes in an experiment, or specifically a statistical experiment. And there are two categories of random variables. Two categories of random variables. Number 1, discrete random variable. And number 2, continuous random variable. A discrete random variable is a variable that can take values that can be counted, like the variable x in our example of tossing or rolling a die. The random variable x that represents the number of dots on the upper face of the die is an example of discrete random variable, because we obtain the values of the random variable x by counting the number of dots on the upper face of the die. Or we say that the values of the random variable x can be placed in a one-to-one correspondence with a set of natural numbers or counting numbers or positive integers. And the values of the discrete random variable can either be finite, as in our example of tossing or rolling a die, or it can be infinite. Example of an discrete random variable that can take infinite values would be the number of years it would take for me to be a billionaire, because that would take many years, infinitely many years, for me to become a billionaire. Other examples of discrete random variables would be the number of vehicular accidents observed daily at a certain road intersection, and the number of new cases of COVID-19 in Las Piñas City recorded on a weekly basis, or the number of defective items counted from a randomly selected sample of newly delivered items. The second type of random variable is known as continuous random variable. The continuous random variable takes values that can be obtained by measurements, and the continuous random variable can have infinitely many values on what is known as the line interval. Consider the real line, where you have the positive real numbers to the right of 0 and the negative real numbers to the left of 0. Just take the interval from 0 to 1 that includes the real numbers 0 and 1. So this interval is what is known as closed interval. And this is an example of what I said earlier of line interval. Between 0 and 1, there are infinitely many real numbers between 0 and 1. And the variable that takes a value on this line interval between 0 and 1 represents what is known as continuous random variable. A continuous random variable takes infinitely many values on a line interval. Examples of continuous random variables would be the number of the amount of energy produced by Meralco per month for the consumption of residents in a certain city, the amount of carbon monoxide in milligrams that is contained in a cubic feet of air, or the distance between the quarantine facilities and the barangays in a certain city. And now we will take probability distribution of discrete random variable. In probability distribution of discrete random variable, we display using a table or formula or chart the possible values of the random variable x and the corresponding probabilities of the values of the random variable x. And if we display these possible values of the random variable x and their corresponding probabilities using a chart, we call it probability histogram. And we will now take an example. For an example, for a probability distribution for discrete random variable, we state the definition of probability distribution for discrete random variable. The probability distribution for a discrete random variable x is a display. This display can be in the form of a formula, a table, or graph or chart. And this display shows the values of the discrete random variable x and their corresponding probabilities denoted by p of x. And these probabilities p of x are the probabilities for the occurrences of the possible random events, the possible outcomes in an experiment, and these outcomes are random events. And when we say random events in an experiment, these events have equal chances of occurring in an experiment. And for each value of the discrete random variable x, there is a corresponding probability denoted by p of x that represents the chances or probability that value of x corresponding to an event in an experiment will occur. And you must take note of the following properties of these probabilities. The probabilities of the events in an experiment to generate the values of the discrete random variable x range from 0 to 1. Or probability p of x is greater than equal to 0 or less than equal to 1. And we have taken this in statistics 1, where we said that a probability of 0 implies impossibility of an event, which means that an event with probability of 0 is impossible to occur. And the highest probability value that can be assigned to an event is 1, which implies that an event with probability of 1 or 100% will occur with certainty. In a probability distribution for discrete random variables, the summation of the probabilities p of x of I, where I is 1 to n, so the values of x, the possible values of the discrete random variable x is n, and for each value of the random variable x, there is a corresponding probability p of x. And if you add up these probabilities, the sum should be 1. These two are used to check if the given table or the given probability distribution represents a probability distribution for discrete variable. If you are given a table and you are asked to check if that table represents a probability distribution for a discrete variable x, you check if the probabilities are greater than, you check if the probabilities satisfy these two conditions. The probability should be positive, greater than 0 but less than 1. And the sum, you add up all the probabilities and the sum of the probabilities should be 1. Now if we present the probability distribution for a discrete random variable x using chart or graph, we call it probability histogram. Now we take an example. Construct the probability distribution, specifically a table, and probability histogram, that is a graph, for the discrete random variable x, representing the number of heads when two balanced coins are tossed. The given experiment involves tossing two balanced coins. So there is coin 1 and coin 2, and we will toss these two balanced coins together. And for each toss, we note the number of heads. And we will construct a probability distribution for the discrete random variable x, representing the number of heads in tossing two balanced coins at the same time. We construct a table to show or display the possible outcomes in the experiment of tossing two balanced coins and their corresponding probabilities. In the first column, we write the events. We represent the events as in statistics 1 with capital letters E with a subscript. There are two coins to be tossed, balanced coins. We denote them by coin 1 and coin 2. And X is the discrete random variable representing the number of heads in each toss of two balanced coins. And P of X, small letter P of X, is the probability of the random variable X. When you toss two balanced coins at the same time, one possibility is you get head in the first coin and head in the second coin. And we denote this outcome for each coin with head by capital letter H. This event of getting head in the first coin and head in the second coin, we denote as event E sub 1. So for this event E1, for this possible outcome event E1, we have H head in the first coin and head in the second coin. Therefore, the value of the discrete random variable X for this particular event 1 is 2. Because the discrete random variable X represents the number of heads when two balanced coins is tossed. And for this particular event, we have 2 heads. So x is 2. Now we calculate the probability of getting 2 heads when we toss 2 balanced coin at the same time. When you toss a coin, there are 2 possible outcomes, and these 2 possible outcomes have the same probability of occurrence. That is, when you toss a balanced coin, either you get heads or tail. And the probability of getting heads is 1 over 2, 1 out of 2 possible outcomes. Similarly, the probability of getting a tail when you toss a balanced coin is 1 over 2, 1 of 2 possible outcomes. And we want the probability of getting 2 heads. The probability of getting 2 heads probability of getting 2 heads can be obtained by multiplication rule for probability. The probability of getting 2 heads in tossing 2 balanced coins at the same time equals the probability of getting heads in the first toss. And in the word "and" in symbols is represented by intersection, and heads in the second toss. The probability of getting 2 heads is equal to the probability of getting heads in the first toss and getting heads in the second toss. And by multiplication principle, this is equal to probability of getting heads in the first toss multiplied by getting the probability of getting heads in the second toss. But as I said earlier, for a single toss of a coin, the probability of getting heads is 1/2. Multiplied by the probability of getting heads in the second toss, 1/2. And 1/2 multiplied by 1/2 is 1/4. Hence, for the first value of the discrete random variable x2, the probability of getting 2 heads is 1 over 4. Another possible outcome when you toss 2 balanced coins at the same time is that you get heads in the first coin and you get tail in the second coin. And we denote this event of getting heads in the first coin and tail in the second coin by event E sub 2. And for this particular event E2 of getting heads in the first coin and tail in the second coin, the value of the random discrete variable x is 1. We are interested in the number of heads when 2 balanced coins are tossed. And for this event E2, the number of heads is 1. We calculate the probability of event E2 in the same way as we calculate the probability of event E1, the event of getting 2 heads, using multiplication principle for probability. Probability of event E2, That is the probability of getting heads. The probability of event E2, that is the event of getting heads in the first toss, in the first coin, and tail in the second coin, is equal to the probability of getting heads in the first coin, and intersection represents and tail in the second coin. And by multiplication principle, the probability of H intersection P is equal to probability of heads multiplied by probability of tail. In the first coin, the probability of getting heads is 1/2, because if you toss the coin 1, there are 2 possible outcomes, and one of them is heads, so 1 out of 2 possible outcomes. And the probability of getting tail in the second coin is also 1/2, because if you toss a single coin, there are 2 possible outcomes, and one of them is tail out of 2 possible outcomes. And 1/2 multiplied by 1/2 is 1/4. Thus, the probability of event E2, the event of getting heads in the first coin and tail in the second coin, is also 1/4. A third possible outcome when you toss 2 balanced coins at the same time is this event where you get tail in the first coin and heads in the second coin. And we denote this event by event E sub 3, the event of getting tail in the first coin and heads in the second coin. And for this particular event, the value of the discrete random variable x is 1, where we get one head in the second coin. Again, our discrete random variable x represents the number of heads when we toss 2 balanced coins at the same time. And for event E3, the number of heads is 1, which occurs in the second coin. And we find the probability of event E3, particularly the probability of x equals 1 for event E3. And that is we calculate the probability of event E2 in the same way that we calculate the probabilities of event E1 and E2. We use the multiplication principle for probabilities. The probability of event E3 equals the probability of getting tail in the first coin and heads in the second coin. And this probability is equal to probability of tail in the first coin multiplied by probability of getting heads in the second coin by multiplication rule or principle. And the probability of getting tail in the first coin is 1/2. The probability of getting heads in the second coin is 1/2. And 1/2 multiplied by 1/2 is 1/4. Hence, the probability of event 3, the event of getting tail in the first coin and heads in the second coin, is 1/4. The last possible outcome when you toss 2 balanced coins at the same time is the event of getting two tails. You get tail in the first point and tail in the second point. For this particular event, we represent this event of getting two tails in both points when they are tossed at the same time by event capital E sub 4. For this particular event, you get two tails in both points. The value of the discrete random variable x representing the number of heads will be 0. And we calculate the probability of event E4. The probability of event P E4 is equal to the probability of getting tail in the first point and getting tail in the second point. By multiplication principle, the probability of getting tail in the first point and tail in the second point equals probability of getting tail in the first point multiplied by probability of getting tail in the second point. The probability of getting tail in the first point is 1 over 2. And the probability of getting tail in the second point is 1 over 2. And 1/2 multiplied by 1/2 is 1 over 4. Thus, the probability of getting two tails when you toss two balanced coins at the same time is 1 over 4. This is the first step when you construct a probability distribution for a discrete random variable x. You list all the possible outcomes, the possible values of the discrete random variable x, and the probability for each value of the random variable x corresponding to the event. Now we summarize this. We write this table more compactly. From this table, you can see that the possible values of the discrete random variable x are 0, 1, or 2. There are three possible values that the discrete random variable x can take. X can be 0, which means you get no heads or heads that do not occur in both coins when you toss two balanced coins at the same time. Or x can take a value of 1, which means that you get one head when you toss two balanced coins at the same time. And you get one head in there are two possibilities where you can get one head. One possibility is represented by event 2, where you get one head in the first point. The other possibility where you get one head is in event 3, where you get one head in the second point. And the third possible value of the discrete random variable x is 2, which means that you get two heads when you toss two balanced coins at the same time. That means you get heads in both of the 2 coins. So we summarize the possible values of the discrete random variable x. The random variable x can take values of 0, 1, or 2. The probability of getting 0 is, from this table, is 1 over 4. Before I continue, I would like to say that if you notice, there are 4 possible events or outcomes when you toss 2 balance coins at the same time and you record the number of heads for each possible outcome. And the probability of, and these 4 possible events have equal probabilities. Each event has a probability of 1 over 4. And that means that each of these 4 events have the same chances of occurrence. That means all the events have the same likelihood of occurrence, and they have the same probability of occurrence of 1 over 4. Now, the value 1 for the discrete random variable x can occur in 2 ways. And we calculate the probability that x will take a value 1 using the addition principle or addition rule for probability. This is the computation to summarize the probability of getting 1 head when you toss 2 balanced coins at the same time. The probability of getting x equals 1 is equal to probability of event E2, or this set operation union is used to represent or event E3. The value x equals 1, or the event of getting 1 head, can occur in 2 ways. Either in event E2, where 1 head occurs in the first coin, or in event E3, where 1 heads occur in point 2. So the probability of getting 1 head is equal to probability of event E2, where head occurs in the first coin, or event E3, where head occurs in the second coin. And by addition rule or addition principle for probability, which we have taken in statistics 1, the probability of event E2 or event E3 equals probability of event E2 plus probability of event E3 minus the probability of E2, event E2, and event E3. Probability of E2 intersection E3 is the probability that both events E2 and E3 can happen or can occur. Now, the probability of event E2 is 1 over 4. plus the probability of event E3, 1 over 4. And the probability of E2, event E2 intersection event E3 is 0. Which means that these two events, the event of getting one head in the first coin and the event of getting one head in the second coin cannot occur at the same time. When you toss two balanced coins at the same time, it's not possible that you will get one head in the first coin and one head in the second coin and the other outcome is tail. Which means that these two events, E2 and E3, are mutually exclusive. Hence, the probability of that event E2 and event E3 will occur at the same time is 0. It is not possible that you will get one head in the first coin and one head in the second coin, and you still have one tail. Which means that the event of getting one head can only occur either in event E2 or event E3, but not in both events E2 and E3. And 1/4 plus 1/4 is 2 over 4. In lowest terms, 2 over 4 is 1 over 2. Divide 2 and 4 by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. Hence, in our summarized table, the probability that x has a value 1 is 1/2. And the last possible value of our discrete random variable x is 2 for event E1, and the probability of that x is 2 is 1/4. Now this is the probability distribution for the discrete random variable x. It's a table that displays or shows the possible values of the discrete random variable x and the corresponding probability for each value of the discrete random variable x. Now to check if your answer is correct, you check if the sum of these probabilities for the values of the discrete random variable x is 1. We check if the summation of the probabilities of the random variable x, where I is from 0 to 2, because the possible values of the discrete random variable x is from 0 to 2. And this is equal to probability of x is 0 probability that the random variable x is equal to 0 is 1 over 4. Plus the probability that the random variable x takes a value of 1 is 1/2. But 1/2 is the same as 2 over 4. You may write 1/2 or 2 over 4. I will write 2 over 4, and the probability that the random variable x will take value 2 is 1 over 4. And And you see the common denominator is 4. That's why I wrote 2 over 4 instead of 1 over 2. So that the three fractions in the sum will have a common denominator of 4. But you may also write 1/2 instead of 2 over 4. And we add the numerators, 1 plus 2 plus 1 is 4. And 4 over 4 is equal to 1. So this is the process for constructing a probability distribution table for a discrete random variable x. We will now draw the probability histogram. We now draw the probability histogram, and to draw the probability histogram, you need the summarized probability distribution table that shows the possible values of the discrete random variable x and the corresponding probabilities. In the probability histogram, we write the values of the discrete random variable x in the horizontal axis. We also denote the horizontal axis with x, and these values of the discrete random variable x are placed in the horizontal axis, equally spaced on the horizontal axis. This is the origin. The 0 here is different from the 0 here. These two zeros are not the same. The 0 here, it represents the origin, the point of intersection of the horizontal axis and the vertical axis. The 0 here represents one of the values of the discrete random variable x. If you do not have 0 as one of the values of the discrete random variable x, suppose you only have 1, 2, 3, then after 0 you start from 1, 2, 3. In the vertical axis, we write the probabilities p of x, probabilities of the values of the discrete random variable x. And you must select a scale for the vertical axis based on the highest and the lowest probabilities. The highest probability here is 1/2 or 0.5. And the lowest probability is 1/4 or 0.25. So I used a 0.25 interval scale for the vertical axis. This is 0.25 or 1/4 plus 0.25 or 1/4 plus 1/4 is 1/2. Now we construct the vertical bars. For the value of x equals 0, the probability of x equals 0 is 1/4. We construct a vertical bar with 0 at the midpoint of the lower base, and the height of the vertical bar corresponds to the probability 1/4. One side of the first vertical bar will coincide with the vertical axis. For x equals 1, when the value of the discrete random variable x is 1, the corresponding probability is 1/2. The second vertical bar will have a common side with the first vertical bar. And we should find 1 at the midpoint of the lower base, and the height of the second vertical bar corresponds to the probability of x equals 1. And finally, for the value 2 of the discrete random variable x, the corresponding probability is 1/4. And the vertical bar for x equals 2 will share a common side with the second vertical bar. We find the 2 at the midpoint of the next vertical bar or third vertical bar, whose height corresponds to 1/4, the probability 1/4 for x equals 2. This is the probability histogram for if the value of the discrete random variable x is 0, the probability of x equals 0 is 1/4. If x equals 1, the probability of getting 1 head is 1/2. Or if x equals 2, the probability of getting 2 heads is 1/4. For your exercise, please try the following problem. Construct a probability distribution for random variable x representing the number of tails when 3 balance points are tossed. Draw the probability histogram. Again, the first step is to construct, to list down all the possible events for this experiment of tossing 3 balance points at the same time and noting the number of tails for each possible outcome or event, and that would be the value of the random variable x representing the number of tails, and calculate the corresponding probability for each value of x. And from the initial table, you summarize the results in this compact table summarizing the possible values of the discrete random variable x and the corresponding probabilities. And from this probability distribution table, you construct the probability histogram, where we write the values, the possible values of the discrete random variable x in the horizontal axis and the probabilities in the vertical axis. In the next lesson, we will take more examples for probability distributions for discrete random variables. If you have a question about the lesson today, please ask your question in the comments below. And do not forget to subscribe to my YouTube channel, Art Kalison, the channel of learning and leisure. Or ask your friends and your classmates to subscribe to my YouTube channel, Art Kalison, so they may learn as well. Thank you for joining me in my class today.